So here's another reaction mechanism, the addition of HX to alkenes. So this same mechanism can work for a few reactants. This example specifically would be hydrochloric acid or hydrobromic acid. So the X is a halogen in this case. Overall, we're adding hydrogen and another group to either side of the double bond here. The mechanism is real important and also kind of helps us keep track of where the products go. So for this mechanism, our nucleophiles are pi electrons here. So those pi electrons will seek out this acidic hydrogen, breaking the bond to chlorine, and we've made a change. So when I'm doing these mechanisms, I like to just redraw the carbon frame that hasn't really changed yet. Right, so all that's in place. Then I'm going to think about where's everything else going to go. Right, HCl bond breaks, so I have Cl minus left over. We'll use that later. And then hydrogen adds to one of these carbon positions. And in general, for this reaction, you'll always, if one carbon atom gets a hydrogen, the other one will get a carbocation, and the carbocation needs to go in the more stable spot. So in this case, the plus charge, so nothing was added here, a hydrogen was added here. And that determines where our product goes because the nucleophile coordination step here, that chlorine is going to end up where the positive charge was. But it's a nice neat reaction because then every atom was used and considered an addition because we've added to the molecule. We haven't taken anything away and we haven't substituted anything off. But where the positive charge ends up is always going to be sort of the key. Also, I forgot to mention it in line, but there is a positive charge here, so it could potentially do a carbocation rearrangement. So that's another thing you need to think about for this mechanism.